Inverse functions. First, before introducing exponential functions, inverse trigonometric functions, logarithms, we introduce the idea of inverse functions in general. Idea, usually we give you a function of with notation, y equals f of x. I like mentioning this idea that x is my input and y is my output. So if y is 3x minus 10, x is 5, then 5 times 3 minus 10 gives me output. And whatever input should give me some kind of output. That's why we call y dependent variable and x is independent. X can be anything in the domain. Grandmothers, cars, units, whatever you want. Y depends on x. Y cannot be chosen anymore because y is a rule, it depends on x. So a question, can I find the input with the given output? That's a very cool question. That's what they call inverse problem. For example, if y equals 3x minus 10, then I can solve for x. Have you ever thought about that? Solving for x. So we're solving for x in terms of y, and we get y equals x equals y plus 10 over 3. And the idea is it reverses the process. In one book for business calculus I was reading for business students, how they explain it, when you get up in the morning, you put clothes on yourself. So you put first, socks, then underpants, then pants, and then a t-shirt. Inverse function reverses the process in exactly the opposite order. First take the shirt off, then pants, then underpants, then socks. And the order should be preserved. That's the idea. So if y function told me take your input and multiply by 3 and then subtract 10, then the inverse function says add 10 and then divide by 3. Kind of cool idea here. We're reversing the process. Reversing the process. Sounds a little bit silly, and we can say now, okay, seems like now y is my input, right? So I found input x in terms of output. Now if I have the result in front of me, y is given, I can plug y in here, and then I will say, okay, if y is 0, it will be 0 plus 10 over 3, 10/3. It gives me x. So in this case, x becomes dependent and y independent. And that's a cool idea of inverse function. Sounds kind of simple, so what? Like, why do we need that? Why do we need this idea? Inverse problems are amazing. Inverse problems actually is a huge part of the scientific world. Many people do dissertations that called inverse problem. Because if we would ever can solve what and how cancer division starts, why cancer starts, why tumor starts growing up, we see the result already. Think about it in medicine. We see a sick person with a huge tumor close to death. What if we could reverse the process in time and see what caused it? If we find what caused the situation, we could fix it, prevent it. So that's the famous inverse problem of the cancer spread. And many scientists fighting with this problem to solve it. And it's very hard. The other one idea, when the tornado is already approaching, it's very late when people are notified by this, right? Somehow tornado just shows up too fast. People are notified and they have like a couple hours to run away. Why? What if we could reverse the process and see what caused the tornado to show up in the first place and then predict it to the future situations? Let people know. Or maybe even pretend, stop it at the beginning. So inverse problems are amazing and they're used everywhere. In the criminology, when the police shows up and they find a dead body, they cannot ask the dead body who killed you. So how do they know how long it stays on the floor being dead and what happened? They use inverse functions. It's all mathematical already calculated. With the temperature of the body they're taking right now, they can calculate, since there's a Newton's law of cooling in the room, you already was introduced to that idea. They know how long it was cooling down, plus the inner temperature of the body, plus they see the chemicals in the blood and so on. They're reversing the process and they can say this person was killed 10 hours ago. How old the Earth is. We never could reverse the time and see when Earth was created, how old it is. They used inverse problems to calculate that. So there are many applications of this, and those are challenging problems. People can get a Nobel Prize for solving inverse problems. Make sense? So that's why we're introducing this to you. It's an amazing idea. Amazing idea. And it works like this. if for each A as an input, 3 was the output, for B, 1 was the output, for C, 2 was the output, inverse reverses the idea. For each 3 as an input, A will be output. For 3, A is the output. For 2, let's connect 2 was about C. Now 2 is my input, C is the output, and so on and so on. Make sense? So that's kind of the idea. And now the big question which is always happen during the conference presentation, when people reveal, we found the inverse for this amazing problem, give me a Nobel Prize. The question is, does it exist though? Well, whatever you did, is it legal? So what the question states is, does it always exist? Does it always exist? Question mark. Which means, can we always find or not? No, we don't, and that's the problem. We cannot always assume there is an inverse problem or it's a unique inverse solution. What if several things cost the same result? And how can you choose that? So first of all, let's introduce the definition of one-to-one functions. And those, the one that resolve the idea, when can you actually find the inverse problem? Definition. One-to-one functions have several notations. Either we actually call it 1, 2, 1, or I like the notation 1 and 1. That's the same thing, 1 to 1. It's just a very nice short notation. F of x is one-to-one function if the outputs do not match. So f of A did not match with f of B, then the inputs should not match either. I will show what it means in a second, but basically it means for one unique input there should be one unique output. And it looks like on those bubbles I just showed you, or you can make a sketch like this. Here's my domain, here's my range. Domain is where my inputs run around, and range is where my outputs run around. So it's basically little worlds for each. For one domain per input, I have one output in my range. For one more, I have exactly one. For one more, I have exactly one. It should not happen that. So this is one-to-one example. And then not one-to-one example. Looks like this. For one input, I have one output. And for the different input, I have the same output. That's what we should avoid. Kind of makes sense. If you imagine a profit and revenue example, you build a business and they ask you, what's your profit for the March? And you said, in March, the profit of the company was $2 million. Also, somehow, what cost this $2 million? And we say, oh, we sold 5 million items. Also, somehow, if we sell 3 million items, it will give me the same profit. That's not convenient. You don't want to have two different inputs giving you the same result. It's just weird. So it's like a dead body on the floor and they're investigating the murder and they say, I think it was killed 5 hours ago, but also maybe 13. That's wrong. Like we want to avoid situations like this. We don't want to have confusions. We want to have exactly one answer for one question. That's what you call one-to-one functions. If function is one-to-one, you can find the inverse problem. So to do that, how to find out? One of the ways to find out is horizontally, using horizontal line test. Horizontal line test. Horizontal line test says horizontal line should intersects the graph or graphs, doesn't matter, not more than once. So we basically make a lot of horizontal lines, intersects the graph not more than once. Then f of x is one-to-one function. this is going to be the main idea how we're going to be checking if we can find the inverse function or not. Here's the example. Here's the graph. And you make a lot of horizontal lines. Horizontal lines. If I do over here, it intersects 0 times. That's why it should be not more than once. Then here once, 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 and once. Everywhere it's once. So if horizontal line test tells me that all horizontal lines intersect the graph of the function not more than once, then we can build an inverse function, and that's like a big deal. That's a big deal. Versus, I don't know, even a circle. We work with circles so often, but actually it's not convenient because it doesn't pass horizontal line test. Either we intersect the circle twice or once or less than that. But the twice is a bad idea. So not 1 to 1. 1 to 1. That's
jump discontinuity.
What?
What about jump discontinuity? Like
good question. You can find if the function is not continuous, it's very good at you even imagining this. It has pieces, like piecewise function. And for each piece which passes the test, you can find the inverse. But then the inverse will be discontinuous as well. That's interesting most of the time. Yeah. It's a very good question that you even imagining how it will be, how it works with pieces. And most of the functions do have some kind of discontinuity, so that's why it's hard to work with them. You have to work carefully piece by piece. Now, finally, we can introduce what does it mean to have inverse function mathematically. Definition. If f is 1 to 1 with the given domain, with the domain A in range B, then inverse function, let me put a green color, this is definition, then inverse function, and here's notation, get used to the new notation, is f to the minus 1. F to the minus 1 is not the same as 1 over f. That's notation of reversing. It means going back, reversing. F minus 1 is the inverse function notation. F minus 1 with domain B. I will explain this in a second. And range A is, and it looks like this, the official definition is, inverse function is now taking my output and using it as an input, and the original input now will be the result. This is double arrow notation, so it goes here and there, or the if and only if, or works both ways. F of x equals y. So see how interesting. X used to be input, now x is the output, and vice versa. Y used to be output, now it's input. That's the definition. Again, let me point this out. I will do it only once. Note. F minus 1, it's not the same as 1 over f. Not the same. It's notation. Minus 1 doesn't mean 1 over f here. So usually if you want to do 1 over f, people put parentheses and then negative 1. If there's no parenthesis with negative 1, that means inverse. So a question to you looking into those bubbles. I'll go back to this in a second. Just want to ask. Look in these bubbles over here. So here's my 1-to-1 function. Here's the domain. Oh, actually, I can make new ones to show you this. So I will do one more green bubble as a domain and one more green bubble as the range. Now the function goes from A to B, which means A is my domain. Input in A gives me some output in B. Input in A gives me B. Input in A gives me B, and they're all unique. So for one input, you have one output. You don't intersect, which is nice. The inverse function reverses the process. So I will take different color. I'm taking the input in my range, and going back in some kind of different way. Like, think about that. The function is not going to be the same. It will reverse the process. You had quadratic, now it might be square root, right? And so on. Takes the input in the range and then gives me back the original input, which now is an output, and so on. And this is notation of f minus 1. In orange, it's f. So tell me, interesting idea. If A is my domain for f, and B is my range for f, and now we're reversing the process, does this make sense that whatever used to be domain now is range, and range becomes a domain? Make sense? Because we're basically mirroring the situation. That's why this phrase here says that f has domain A and range B, but f minus 1 has domain B and range A, because it flips the situation. It mirrors it. Whoever comes in and whoever comes out changes places. That's the idea. Ask me, does that make sense? Good job. Then, to point out this, what do you think gonna happen if I'm taking the inverse function and applying it to the original function with x? What do you think the result is going to be? X. Can you explain why do you think so? Like, I would look at this graph, like, even, right? How would you explain it?
Actually, like, first, for one input, it's 1.21 output, and then we're passing it out again, so it will like do that.
Yeah, exactly, exactly. So he's saying, if I used to have x over here, it go, so f of, the first step is the function inside, you know that, right? We always start from inside. So f of x goes to domain B, to the range B over here, and gives me f of x. Then the inverse function tells me, okay, now take that result and bring it back. So it brings me back in some kind of different rule, and then what will be the answer? Whatever we started with, x. Make sense? That's the example of the dressing up and undressing the guy from the Business Calculus book. Oh, seriously, it's funny that only Business Calculus book has this kind of example. So you was naked at the beginning. You put clothes on in some kind of order. When you take it off, you reverse the order. You was naked at the beginning, you'll end up to be naked at the end. Make sense? So like, that's the point over here. So the answer is x. Good job. X. Same idea if you do f and apply it to the inverse with x, the result will be x as well. The difference is what my x is. In the first case, x is in the domain of normal function, which is f. So in a domain f. But in the second case, look how we're starting. We're starting with an inverse function. So the original domain actually is whatever is domain for the inverse. X is in the domain of inverse. For now, it's a little bit confusing. Here's the explanation for you guys. So, in the grocery store, in 7 in the morning, sometimes you might notice a lot of old people there. Like, somehow they just like to go grocery very early in the morning. You know, like you go there, and then, so there's a whole statistics, or maybe even a study that says, I wonder, like, how many old people are coming to the grocery store in the morning, and maybe I should put corresponding products closer to them, not to walk deep down into Walmart and so on, but like grab what they need based on the data. So that's what data science tells us. We collect the data, so we know. So my inputs are, let's say, old people, right? And the output will be how many tomatoes I should put in the first row. So think about that. So input, which is domain, number of old people. Output, number of tomatoes. So this is completely different things. Completely different things. Even ethically and understanding amount of those things is different. What they do is different. One is life, the other one is an object, and so on. So reversing it means if I know I have 10,000 tomatoes in the first row, I wonder, will it attract more old people next morning? Does it make sense? So you should not mix this up. If x is in domain of f, it means we're talking about how many old people are coming. If x in a domain of f inverse, we're talking about tomatoes. That's why it's important. You should not mix this up. You mix this up, you're not making a model realistic anymore. So you should be careful with this. Put it in the box. Okay, good. In my country, since the public transportation is very popular, we make jokes that at 7 in the morning somehow old people have to go somewhere. And like all public transportation are full of old people. And since students have to go to school, there's always a conflict. Why there's so many people in the bus? And then we never understand why they always have to go somewhere in the morning. Just wait a little bit and then go, because students don't have a choice. We have to go to school. There's always a conflict about that. Graphing. Graphing. How to graph an inverse function. So when you have original function f, then just reflect it. Reflect original function about a mirror. That's how I call it, but basically it's not a mirror, it's a line about the line called y equals x. Y equals x will serve you as a mirror. That's the idea. Reflect if you can find it. Again, you first have to check. So don't reflect anything you see. You first have to check if it's even possible to find it. And then, when it's possible, you will see something like this. X squared and square root of x. Makes sense? So x squared, how to undo squaring the x? You're using a square root. How to find the inverse of each other? You build y equals x. That's the dashed line. And then you reflect graph with respect to this dashed line. And that gives you a very nice looking inverse function graphically. So that's how people find it graphically.
What's an example of a function that wouldn't be able to find?
Yes. Good job. Spoiler alert, you ask exactly what I want to say right now. Like right now. So examples. But I wanted to ask a question. And now you kind of spoiled the situation. But my question was, is this function... And does this function has an inverse? Example. Finally, let's do the example to make it more interesting. Example, y equals x squared. Such simple example. What's the problem with that? Does this has an inverse function? I just literally show you the graph. So probably you think, duh, it was x squared of x. Wrong answer. X squared actually is not that simple. What is x squared? Graphically, how do you call it? How do you call it graphically? Parabola. That's what I hoped you're gonna say, but okay. Parabola. Yes, it's a parabola. We all know it. Does it pass a horizontal line test? No, it doesn't. It doesn't pass a horizontal line test. So actually, this one is not 1-to-1. So thus, there is no inverse. But I just show you the animation. That's very interesting. That's a weird about. So that's where scientists come in and they say, don't panic, let's think about it. And that's what we try to teach you. We try to teach you to think critically, not just follow the rules, but to have all this knowledge you're accumulating from college and now ask cool questions and offer cool solutions. Which might sound crazy first, but maybe we can fix the parabola, and when we fix it, we can find the inverse function. How about that? And by fixing it, there's a terminology that's called let's restrict the domain. Restrict the domain. The domain for parabola is minus infinity to infinity. Anything I want, I can plug into x here. Minus pi over square root of 2, I can plug it in. Plus million, I can plug it in. But then I cannot find the inverse function. Then the idea is, what if instead of using the whole cup, which parabola looks like a cup, when it's concave up, we're going to learn what it means. What if we just use 1/2 of it? Left or right? Does it pass the horizontal line test? And that means from the function which you cannot use, you can create a function which you can use. And if this function will help us to solve a cancer problem, that would be amazing. So that's a very decent idea, right? Fine, it will be not fair anymore, but you can kind of glue it into pieces, leave only the interval you need, work on that interval, and then work on another interval separately. And then create two different inverse problems. Because for each side, it passes a horizontal line test 1-to-1, so inverse exists. It's still x squared. Think about that. That's maybe new if you've never seen this before, but it's x squared that has a different domain. We're now not allowing negative numbers. Make sense? We can start from 0 to infinity. And that's what we call restricting the domain. Restricting the domain.
You know what, right? That's restricting the domain.
What?
Where you only did the half of the...
I will show you how to write it down. How to write down the half of x squared. It's half only on the graph, but on the written part where we write the expression of the function, it's still y equals x squared. My job is just to let mathematics know that I'm changing something. And what did I change? Originally, the domain was negative infinity plus infinity. That was the domain over here. So the only thing I changed, I restricted the domain. And the domain now is new domain. I will do like this. New domain is 0, and you can choose include 0 or not include 0, depends on the situation, to plus infinity. For this one, I will do like this. Restricting the domain helps. Helps quite a lot. We will have trigonometric functions that do the same thing. For this new function, the inverse exists. Since I mentioned trigonometric function, have you ever heard about arcsine, arccosine? Well, excuse me, this thing doesn't pass a horizontal line at all, right? So, like it's supposed to hit you right now. Wait, sine and cosine cannot have inverse functions because both of them do not pass horizontal line test. How come we know from high school about arcsine, arccosine? Arcsine and arccosine literally undoing what sine and cosine do, so they are by definition inverse functions. They work because we're going to restrict the domain at some piece, from some piece to another piece, where it passes the horizontal line test, and we're going to say arccosine and arcsine exist only over here, on that interval. And that's why maybe you remember from the table, arcsine, arccosine, arctangent exist on a different interval because of that. Because of all this proof when we can even find the inverse function. So now it will look like this. First of all, look back to this graph. Here it is. When they show x squared over here, didn't you think about it? X squared in the blue color is not a full parabola. Where's the left-hand side piece? So what they did not write below is that one is not from minus infinity to plus infinity. It's from 0 to plus infinity, which makes sense now because square root does not exist from negative numbers. Make sense? So square root, this guy, cannot exist for -5, but there's no -5 here. We cut it off. Let's do it. We're gonna have Cartesian coordinate again here. Now I don't need left hand side, so you don't have to even draw it if you don't want to. Only right side of y equals x squared from 0 to plus infinity, restricted domain. Now I'm drawing the mirror function, which is y over x. Y equals x. Dash, 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 dash. This is a tool. That's why we use using dashes there. It's not a function we're going to use. We're not going to use it in calculations. It's a tool. It's used as a mirror. So you know how y equals x squared looks like. It's like a cup. Now reflect using this mirror. Whatever was input over here will become output over here becomes output over here. And so on. It reflects, touches y equals x at the same place, and keep going. And this pink part, or this purple part, exactly looks like what? Y equals square root of x. Make sense? You remember how y equals square root of x looks like. So f of x is square root of x. That's a new function. We basically just created it. Let's do x squared first. X squared. Domain. What is domain and range? Domain used to be minus infinity, plus infinity, but we restricted it to 0. 0 and plus infinity. What is the range? It starts from 0 and goes up forever. So it seems like it's never negative, right? Because x squared is never negative. So domain and range are 0 plus infinity. Then, when we created a new function, that's one piece, a new function which called inverse, f inverse, equals square root of x. And here you're supposed to ask me, wait, didn't you just say that x and y change places? It changed places, so actually it's supposed to be square root of y over here, and then x, but then we're just renaming it. It's not convenient to see it, f of y. Yeah, square root of y and so on. It's not convenient to see it this way, so people just renaming, because you can always rename the variable. It's not illegal to do it this way. So just to be convenient, we still call it square root of x. Then put it in the box. That's my inverse. For this inverse, domain and range should switch orders. So whatever was domain for the first function will be range for the second function. Range for the square root of x, 0 to infinity. Whatever was range for the first function now becomes domain for the second function. 0 to plus infinity. That makes sense because square root does not exist for negative numbers. And that's how these functions were created. And on Wednesday, we're going to talk about e to the x and log. They are inverse to each other. How they were created. It's actually an interesting story of mathematics over here. Ask me questions. Do you like this graph? What do you think about this? What kind of feelings do you have about this? Looks not too bad, but now we're going to introduce you more complicated material, which is finding derivative of the inverse function and actually finding the inverse function. Finding the inverse function is not too bad. I'll give you steps. You can follow them. It's not too bad. Example 2. What if a function f of x is x cubed plus 2? Find, and we ask you, find the inverse. Find the inverse. So the idea is we ask you to undo the situation, to undo whatever is happening. But first you need to check if it exists. Probably if we ask you to find, probably it exists. But just actually you're supposed to check. Cube function looks like this, right? It's like a chair. Plus 2 means it shifted. Yeah, the chair definitely passes the horizontal line test. So it is 1-to-1 everywhere. 1-to-1 function. That's the notation 1-to-1. Thus, inverse exists. How to find it? Okay, let's do it. There are several ways we see it. Step 1. Write down in the form of y equals x cubed plus 2. That's just easier this way. Step 2. Basically, you want to solve for x. That's the whole idea. Solve for x. To do that, try to isolate x cube or whatever you have, square root of x, sine of x. Try to isolate this piece with x. We're solving for x. Okay, let's do it. X cubed equals y minus 2. X equals a cube root y minus 2. And then the last step, we usually ask you to rewrite. Step 3. Kind of interchange or rename. Interchange or rename x and y to have a nice answer. Then the inverse function will be, the answer will be f inverse of x. Well, renaming gives me, let me not skip this step. Renaming becomes y equals cube root x minus 2. That's what we mean by rename. Whatever used to be x becomes y, whatever used to be y becomes x, because input becomes output, output becomes input, and then whatever you just found, that's inverse. Inverse function is cube root x minus 2. That's the answer. You can also say it out loud to yourself. It actually makes sense. The original function was take your input, cube it, and then add 2. Then the new function will be you undoing with the same process backwards. When we added 2, now I want to subtract 2 first. Then it says cube the input. Then I will take a cube root of the result. Make sense? It's exactly the same order, just reversed. That's what we're doing here. And that's inverse. Inverse function. You can do it. This problem is actually not too bad, just a little bit of patience and algebra. Some algebra, move things, divide things, find roots, and so on. What new thing coming is how to find derivative. Theorem tells us that actually there's a shortcut to find a derivative of the inverse function. Theorem says if f is 1 to 1, that means it has inverse function, and has a derivative. Has a derivative means a differentiable. And differentiable. If f is 1 to 1 and differentiable means has a derivative with the inverse, f minus 1, then f inverse differentiable as well, and that's good because derivative, as I try to keep pointing out all the time, means how fast something is changing, how fast the progress is going. Derivative also predicts future and shows you the past. So we don't have to wait for millions of years to see how far the Mars is. We can calculate the distance and the speed of its movement doing derivatives, looking into the future, or looking into the past to see what happened with dinosaurs and so on. So it would be nice if I solved the inverse problem, if I solved why there is in Sedona, there is a crater after the volcano, right? You know that? There was used to be a volcano there and it erupted, blah, blah, blah. How do we know all of this? We solved the inverse problem. That's why archaeology actually uses mathematics and some equations there to solve inverse problems. So we solved it, and now I want to know how fast the eruption happened. It would be nice to do it without finding the inverse function, because sometimes it's very hard to find the inverse function. Can I find how fast the inverse function is without finding the inverse function? Without finding the derivative of the original function. The formula is, I'll write, yeah? This is, so -1 and then prime derivatives. Yes, they asked me definitely. So it's like this. It's differentiable as well, and how to find it. And the formula is the derivative of the inverse function at a is 1 over the derivative at, find it at, take another color if you have, or a pencil, that will be easier to see in the future, inverse at a. Inverse at a, of course if denominator is not 0, then, or it doesn't make sense even to start, if this is not 0. And this is the formula, you'll have to remember it. It's probably gonna go to the test, and you will have a lot of homework problems for that. So, example, exactly the last 5 minutes to do the example on this. And you'll see what I mean, why it's actually a convenient way to find a derivative. 2x plus cosine x. The thing is, just like I told you, finding the inverse function is complicated. Most of the time. Most of the time it's not just -2 and then take a cube root. Most of the time there's going to be, how would you find inverse function for this? 2x plus cosine. There is an arc cosine involved and division by 2. How would you do it in the same time? So for this one, we can't find f minus 1 directly. But we can, but using the theorem, we can find the derivative. Oh, that's not prime. That's inverse. Be careful here, that's inverse. Let me put a red color. We can't find inverse directly, but using the theorem, we can find the derivative of this unknown function using the formula. And this is how it looks like. Step 1. What you do here is you use a theorem and you're saying, okay, we were looking at, oh, the question is find the derivative of the inverse function at 1. Okay, find this. The derivative of the inverse function at 1. So this is what we're going to say. Looking for a derivative, looking for the inverse function without a derivative at 1 means looking for some kind of b. We're going to call it b. Why do we need this? Because it's over here in the formula. Inverse function at the given point. But we don't have inverse function. Can we avoid the step finding inverse function and plugging a in it? Yes, we can. Inverse function at 1 equals b means, that means by the definition, which we introduced today, f of b is 1. Make sense? So inverse of 1 equals b means f of b equals 1. We're just exchanging these two guys, 1 and b, and renaming the function inverse versus the original. Then let's plug b into the function we have. What function we're talking about? We're talking about 2x plus cosine x. Step 2. Plug b everywhere you see x. 2 times b plus cosine b, and we know the result. It's 1. That's exactly what I'm talking about. What if you know the result and you're looking for the input? This is exactly the inverse problem. I know the answer is 1, but I don't know the input. That's why I call it b. You can call it, you don't want to call it y or x because those are already taken. You can call it t, m, whatever you like. Just b is convenient. b, cosine of b plus 2b equals 1. Well, you need to solve this somehow. And step 3 in this case, let's do it this way. Let's find the derivative of this. The derivative of x in general is 2 minus sine x. So those two things are coming from the original function. Those two things are coming from the original function. I'll put it from this orange part over here. That's what we know. Finally, I can plug things here this way. For f inverse prime, by the definition, is 1 over f prime, so 1 over, this is the formula, f prime at f minus 1 of a, f minus 1 of 1. Well, when this number 2 equation holds, cosine of what gives you 1? Cosine of 0 gives you 1. 0 times 2 is 0, so actually it will work. If I have 0 plus 1 equals 1, it works. So b is 0, and this is how I'm going to use it. Sometimes, if you have the result, but you don't have the input, you can guess. Or if A, you can make a good guess. Or B, it makes sense to just list possible solutions. And in this case, B equals 0 works. So this thing inside actually is 0. We're almost done. Just a second. Then it becomes 1 over f prime at 0. F prime comes from the number 3. That means I will have 2 minus sine of 0. And that we can calculate. That is 1/2. And this is the result. Super confusing. I know right now you just completely lost. Which is usually the case for the example for the inverse derivative. What we did is, without finding the inverse of the original function, we found the speed of the derivative of the inverse. How fast my inverse is. 1/2 fast. Positive means the inverse is increasing without knowing what inverse is. Practice these steps at home and you will get better at this. Couple examples should make you good.